I should say I'm not sure quite how long this will go, so if it starts going too long, you should feel free to jump in and
It's okay. We have no. Fayard and Eugene L. Langberg, professor of physics, and also the co-director of the Center for Particle Cosmology at the University of Pennsylvania. Today, he will be talking about gravity and cosmology, its classic successes, and recent challenges it has faced. So, before we start, a few norms that we follow here. We shall have our cameras and microphones switched off at all times, and we shall also unmute ourselves when asking questions, which we will have at the end of the lecture. So I would appreciate it if everybody keeps their lectures, if their questions to the end. You can start now.
okay, let me see if this works this time. How's that?
Yes, we can see that.
Okay. Well, thank you for having me. It's a pleasure to be here to give this talk. I was told the audience was very broad, mostly scientists, engineers, physicists, undergraduates. So I'm not quite sure of everyone's level of presentation. So I'm going to apologize in advance if I miss any of you with some of this. But certainly, as was said, we'll have questions at the end. But if there's something on the way that is just completely insurmountable, feel free to ask a clarifying question as I go along. Okay, so I want to talk to you about gravity, and in particular, I want to talk to you about the relationship between gravity and cosmology, both a little bit historically, and then also what it means in this very exciting period we're in right now, where we've sort of just launched this era of what I'd call gravitational wave astronomy. So to do that, I'm going to need to tell you what gravity is, and that's actually quite difficult because gravity, in the sense that I mean it, is described by Einstein's theory of general relativity. And most people haven't taken a course in general relativity. So I'm going to start by trying to teach you general relativity in a few slides. And of course, I don't really mean that, but what I mean is I'm going to try to give you enough information based on some things I think you probably know, or at least most of you know, to carry you along for the important parts of what I want to say in the rest of my talk. So I'm going to start by doing that. Then I'm going to comment a little bit on things we know about general relativity and how we know them from the past. And then I wanted to talk about cosmology as a test of GR, and in particular, general relativity as a tool in cosmology, and in particular, how it tells us about things like dark matter and the missing components of the universe. And then I'm going to sort of jump forward and talk about the universe both in the very far past and what that means about inflation as a very sort of futuristic thing. Inflation is something I'll introduce as a test of the quantum nature of general relativity. So one of the holy grails of theoretical physics is to understand quantum gravity, and it turns out that understanding the role of gravity in cosmology may be one of our best chances to unlock that particular puzzle. And then at the end, I'll just try to talk a little bit about some of the recent developments in gravitational wave astronomy and what that might hint at for the future of understanding gravity in cosmology. Okay, so I'm going to start by assuming that you know a little bit about special relativity, but not a lot. And then I'm going to use that to just teach you about general relativity. So if you've taken special relativity, you know that everything you want to know about special relativity is described by the light cone. Observations of different observers are related by what are called Lorentz transformations, and light rays always travel at 45 degrees. So this is something you learn. The speed of light is constant. It's something you learn as an undergraduate. But for our purposes, it's enough to know that all of the physics of special relativity is encapsulated in something we call the line element. And I've written it out here in some complicated notation, which we don't need to know for my talk. But let me just say a little bit about what this is. The first things you learn in physics are Newton's laws and things like that. And those all obey sort of what we call a Galilean theory of symmetries, meaning that if you know everything about how distances behave, that's enough to really construct the symmetries of the sort of old way of doing physics. So what do I mean by that? Well, if you take Pythagoras' theorem, I've got 3 points on the floor that make a triangle, and I draw lines between them to make a right angle triangle. Then we know that the square of the length of the hypotenuse is equal to the square of the sums of the other sides. And we know that the distance between 2 points is invariant. So if you measure the distance between 2 points, it doesn't matter what coordinates you use to measure it in. Special relativity is not so different to that, except special relativity, as Einstein taught us, introduces time. And so in time, in special relativity, we have something that looks a little bit like a line element, but we call it ds squared, and it involves both the Pythagorean distance in time and the time itself with a different sign. Sometimes we encapsulate this in a little cute notation like this, where we say eta mu nu times dx mu dx nu, where you add up all the indices. So this is -1 times dt dt, +1 times dx dx, +1 times dy dy, etc. So actually, could I ask, can you see my pointer when I'm moving it around?
Yes, sir, we can see.
Okay, great. Okay. So this is how special relativity works. And we won't talk about the physics of special relativity here. I just want to lay out that notation. But the important thing is special relativity does not include gravity. And of course, when Einstein came along and he tried to introduce gravity, he encountered some fundamental problems. And I want to explain what those are and how they sort of point us in the right direction of how we might have a theory of gravity. So we all know that if you take a couple of rubber balls, perfectly rubber balls on a perfectly bouncy floor, and you hold them in your hands and you drop them, that they start off at 0 kinetic energy and a certain amount of gravitational potential energy. And then if we drop those balls, then they will fall to the floor, their kinetic energy will increase, their potential energy will decrease, they will hit the floor, reverse direction, now they'll start climbing, their kinetic energy will start decreasing, their potential energy will start increasing. And when they reach the point at which you originally let them go, then they'll have 0 kinetic energy and they'll come to a stop. And the reason this happens, the underlying reason that this happens, is conservation of energy. And it's not very mysterious to any of us, I would expect, who are in this talk. Now, you can ask, it turns out you can ask a similar question about particles that are not bouncy rubber balls, but are elementary particles such as the electron and its antiparticle, the positron. So here I've got a little thought experiment for you. I'm going to take an electron and a positron. I'm going to let them drop down and bounce off and how do you bounce particles like this? You'll see in a moment, bounce off the floor and come back up. But the way I'm going to do it is I'm going to allow them to annihilate into light, have the light bounce off mirrors, and then the light come back up and recombine and produce an electron and a positron. So this is the kind of idea I have in mind, and I can let them produce. Now, of course, the strange thing about this is that, let me do that again, when I originally dropped them, they're massive particles, and of course, they fall in a field, in a gravitational field, just the way we talked about rubber balls. They're gaining kinetic energy and losing potential energy. But once they become light, normal Newtonian gravity doesn't act on light. And so the light can do whatever it wants. So it comes down, it bounces off the mirrors, it goes up as high as you like, nothing happens to it. And eventually I can just smash it together and make these particles again. So here, nothing's happening to the light, and then they produce the particles. So this gives you some kind of pause, because you should worry that what I've done here is I've started off with two particles at one height, not moving, and ended up with the same two particles at a higher height, not moving, and I've violated conservation of energy. And in fact, that's a real problem. If you allow this to happen, you would violate conservation of energy. So the way you can solve this is by hypothesizing that when this is happening, when light is dropping in the gravitational field and rising in the gravitational field, it is also affected by gravity. So the way to recover conservation of energy is to hypothesize that light must gain energy when it's falling in a gravitational field and lose it when it's climbing in a gravitational field. And if you've studied at all light in your courses, you will know that the only way that light can gain or lose energy is by decreasing or increasing its frequency as it moves. And so what we've learned here is something very profound, which is if you want to preserve conservation of energy in the context of special relativity and quantum mechanics, then the only way to do it is to demand that light be affected by gravity, and do so by changing its frequency as it falls or rises in a gravitational field. And this notion is something that we call gravitational redshift. So keep that in mind. Now let's do another thought experiment. I want to imagine we're sending a pulse of light from the surface of the Earth, or the sun, let's say in this case, all the way to Earth. And I've drawn the light here, and you'll see why I've drawn it that way in a moment. So a light wave is emitted from, say, the surface of the sun. Sun is a big, massive body. It's got a heavy gravitational field, and the light has to climb out of that potential well and come to the Earth. Now, if you try to draw a special relativity space-time diagram for this, let's call that distance between the sun and the Earth h, and let's draw a diagram. We always draw space horizontally in these diagrams and time up. And remember what I told you about special relativity. Light rays always travel at 45 degrees. In other words, light travels at a constant speed. So I'm just going to focus on the peaks of the light wave and trace their traveling from the sun to the Earth, and the light rays must travel at 45 degrees, so these are all parallel. But now this is a problem for me, because if I ask what is the period, if you like, the distance between the peaks of the light wave when it's emitted, and the distance between the peaks of the light wave where they're observed, you'll immediately see that they have to be the same, because the light rays traveled at 45 degrees. Light traveled at a constant speed. And of course, this period is inversely related to the frequency. And so it is not possible that our hypothesis that light gain energy or lose energy in a gravitational field is consistent with special relativity. So we have a problem. We have an actual inconsistency. You cannot retain conservation of energy, which is sacred in these situations, and have special relativity with gravity. You might try to fix this, okay? You might say, well, maybe that's what happens, right? That it falls and it rises in a gravitational field, the period gets bigger. But then the light rays are not traveling at 45 degrees, and you've violated special relativity, okay? So how could you do that? What can you do in this situation? And then what you can do is you can have to modify special relativity, right? Special relativity is based on the notion of a global inertial frame. Namely, you set light rays off at 45 degrees in that diagram from one point, and they arrive at 45 degrees in the other point, in the other place. The way you could fix this is if that wasn't true. If the only way you could measure times and distances in general is that you can measure them differently at different points of space-time. The only way to do that, to take you back to special relativity, is if I take this line element. This is the thing that told me that light always travels at 45 degrees. And that's a constant. Right here, this is just a collection of numbers. It's a -1, a +1, a +1, and a +1. That can't be good enough because this forces me not to be able to change the frequency of light. Somebody has their microphone on? Thank you. So one way to do this is to replace the GR line element, replace this line element by what we call the general relativity line element. Literally promote this object to be a function. And this might look like sort of abstract notation, but don't worry so much about that. All this means is that when you measure something, like say the frequency of light, measuring it at one place, like at the surface of the sun when it's emitted, and measuring it at another place in space-time, at the surface of the Earth when it's measured, can have different results. Okay, this object here gets as a name, it's called a metric because it's the thing that helps us measure things. And it tells us how to measure changes in time and distance at different points in space and time. So what we've tried to make an argument for here is that if you want to retain something like conservation of energy, and if you want to have gravity involved, then you must abandon special relativity and replace it with something a little more general that allows for measuring things differently at different points in space and time. So what is general relativity? What is Einstein's most famous accomplishment? Einstein's most famous accomplishment is writing down the theory, general relativity, that tells us how, given what the distribution of mass and energy is, in the example I gave you, the sun, how to associate a particular metric with that distribution of mass and energy. In other words, you tell me I'm interested in sending light from a big heavy object like the sun. General relativity gives you a bunch of differential equations to solve. You solve them for this thing called the metric, and then the metric tells you how to measure distances and times from place to place. If you do that correctly in Einstein's theory, it will tell you that light changes its frequency as it climbs out of a gravitational potential well or as it falls into a gravitational potential well. So general relativity is a set of equations. Don't worry, we're not going to solve any equations in this talk, but I just want to write it out schematically. General relativity says that a bunch of differential equations for an object called a metric are sourced by the matter and energy in the universe. You just solve these equations. They're very complicated, they're very nonlinear, and you spit out something called the metric. And that metric then imparts a set of rules to the laws of physics in this new framework. Matter moves along straight lines in what's called the curved up space described by this metric. This is a metric that changes from place to place, and so it describes a space that is not flat like the space-time of special relativity, but is curved. And in general relativity, this is the reason that planets orbit the sun, and as we'll see in a moment, it's the reason why the universe expands. So that is my lightning introduction to just the key notions of general relativity. Does anyone have any important questions at this point before I move on? Okay, so let's talk about how general relativity was tested. So over about a 50-year period, over a century ago, what's now a very familiar argument played out. People were looking at the way in which Mercury, the innermost planet, went around the sun, and they noticed that unlike predicted from Kepler's laws, from Newton's laws, it did not go around the sun in just a plain ellipse, but the ellipse itself precessed around the sun. And this is a very exaggerated picture that I'm using here. And in fact, Leverrier came along and said, okay, well, we know that this is odd. and we know that it doesn't agree with Newton's laws, but you don't have to abandon the laws of physics. Maybe what's going on is there's some other planets other than us on the interior of Mercury's orbit. They're on the other side of the sun from us, and we don't see them. But the gravitational perturbations they inflict on Mercury as it goes around the sun are enough just to change its motion and make it undergo this precession. And this was a very popular idea at the time. And you can think of it in many ways as a suggestion of some sort of dark matter, because it's matter that is gravitationally affecting Mercury, and yet you can't see it. But in fact, we know now that this was not the answer. And once Einstein had written down the theory of general relativity, you could see that when you compute orbits of planets, for example, in general relativity, they are very close to the behavior in Newton's laws, but not quite. And the difference is exactly this, that planets precess around the sun. It's a very beautiful fact, and it's what is really a post-diction of general relativity, because we already knew this data before general relativity existed. It's worth pointing out that this has some similarities with the dark matter and cosmic acceleration questions that we face today in cosmology, and I'll just leave that point there in text, and maybe in the questions, if there are people who know more about that, I'd be happy to talk about it. So that's one test on small scales, meaning the solar system. What about tests on the largest scale, cosmology? After all, before Einstein, we didn't really know how to talk about cosmology at all. People had words that they used, cosmology and the universe, but they did not really have a framework in which scientific framework in which those words had any real sense. But after Einstein, they do, because after all, what is the universe but all of space and time? And if space and time can change from place to place, then it's a dynamical object, and the universe itself is now open to scientific query. So I told you general relativity is very complicated, but it turns out in cosmology, on the largest scales, it's very, very simple. Remember special relativity. Special relativity had a line element like this that looked like squared plus this stuff. That's between points in space. Okay. So following this mathematical object up here really is telling you this. You take the universe on the largest scales and you say, well, it's full of stuff, matter, radiation, whatever. But on the largest scales, you can just average over it and it looks evenly distributed. And therefore, nothing really is different from one place to another. The only thing that matters is time. And so then what Einstein tells you is, you tell me what that stuff is in the universe. And then what this metric tells me is, if I've got two points in space separated at time t1, there's a distance between them. One's at point x, one's at point y. You ask, what's the distance between them at point time t1? Then this theory tells you it's given by the coordinate distance, x minus y, and then you just multiply whatever the value of this function is at that time. That doesn't seem very interesting. After all, it's just a distance. But what's interesting is, remember, this depends on time. And what Einstein taught us is that at later times in the universe, what will happen is this. The points will move apart or together, but in this case apart. And the distance between them at a later time will not be the same as it was at an earlier time. It's now measured by the same coordinate distance, but this function at a different time. So this function A, just a simple function of time, encodes how distances change in the universe over time. And the rate at which A increases or the rate at which A increases or decreases, sorry about that. The rate at which A increases or decreases depends on how much matter, radiation, other weird stuff is in the universe. And it's Einstein's equations, Einstein's general relativity, that tells us how to solve for this function A of t, depending on what the stuff of the universe is. So what was the first thing this was applied to? Well, first thing it was applied to was galaxies. So galaxies are beautiful things, of course. They're bright and multicolored and have wonderful morphologies and are wonderful. But for cosmologists, really, they're just dust. You'll all remember, probably in high school, maybe in university, studying magnetic fields by taking a sheet of paper or something, putting a magnet underneath it and sprinkling iron filings on the paper. And then you shake it and you notice that the iron filings show you where the magnetic field goes. For cosmologists, the galaxies are nothing but the iron filings of the universe. They're out there, they're massive, and you look at what they do, and that tells you what space and time is doing underneath it. So for me, they're just a clue. Okay. So Hubble came along in the early part of the 20th century and asked, what are galaxies doing? If we look out there and we measure galaxies carefully, what does it tell us about the underlying behavior of space and time? And to understand this, we need to know a little bit about the Doppler effect. And I'm sure you all know this, but I'll just cover this very quickly. Okay, the Doppler effect is a thing where let me step back from this, first of all, is if you have a sound at a fixed frequency, say a car is going along the road and its engine is emitting a certain note, then what will happen is as it's emitting that note, as it comes towards you, the sound waves get crushed up and the pitch goes up. And as it moves away from you, the sound waves get spread out and the pitch goes down. And here's an example of that happening. This car with its horn. So you hear that, the pitch goes up and then the pitch goes down. Okay. So it turns out that this doesn't only work for sound, it works for light. So if you have a light source emitting, say, monochromatic light, let's just say white light, and you move that source towards one direction, then of course the analog of pitch for light is color. And what you'll see is that here's the light source, it emits light isotropically, it's all the same color. And now as that light source starts to move in one direction, the frequency changes, and in front of the light source, things become very blue, and behind it, they become very red. And those colors are important. If you have light that is in the middle of the visible spectrum, and then you move that source towards something, it becomes more blue. And if you move it away from something, it becomes more red. And this is why earlier we actually called this thing redshift. Okay, so if something's moving away from you and you knew its color, if its color that you observed looked more red, you'd know it was moving away from you. So this is exactly what Hubble did. Hubble again here, sitting rigid-backed. This is one of the only photos without a pipe, I guess, at the Hooker telescope on Mount Wilson. And he's looking at distant galaxies. And he's just asking, those galaxies are composed of stars like our own star. They emit light like our own star. There are specific frequencies of light that you can identify in the spectrum of stars. And then you ask, is the color of that light shifted towards the red? Is the object moving away from us? Or is it shifted towards the blue? Is it moving towards us? And certainly prior to this, I think the notion was that the universe is static, things are moving towards us or away from us, just depending on local gravitational behavior. And you'd see some red and some blue shifted behavior. So what does Hubble see? Well, he found a remarkable result. Here's Hubble's original data. He was a genius because he drew a straight line through this data, which I certainly would not know how to as a theorist. I would draw something like this. But Hubble drew a straight line. And if you were worried about whether Hubble cheated, you needn't be, because we can come along many decades later. And what we're seeing here, by the way, is the distance to distant galaxies measured in astronomers' units, megaparsecs, versus velocity in kilometers per second as measured by their redshift. And you can come along and get much more accurate data, of course, closer to the present day, out to very distant distances. And all this falls along a beautiful straight line. So when someone tells you that the universe is expanding, this is what they mean. They mean that when you look at distant objects in the universe, they're all moving away from us. And the further away they are, the faster they're moving. Okay? All distant galaxies recede from us. We see them redshifting, and their speeds are proportional to their distances. And it's a remarkable observation and one of the most wonderful things I think we've ever learned in modern science. And what this means is that, that you can do the opposite. If you know that this is true, now if you see an object in the universe, a galaxy, and you know its speed, which is easy to measure from redshift, you can look at it, you can look at its speed and infer its distance. And so until really this point, we would look at the night sky and it just looked like it was painted on a sphere. We had no way to tell whether, say, bigger objects were truly bigger than smaller objects or just closer, because we didn't know how to figure out how far away things were. So gazing at the night sky is like looking at the pages of a new book spread out in front of you on your desk in a completely random two-dimensional pattern. And what this relationship allows you to do is sort of read the page numbers on that book. It allows you to put the book of the universe back in its correct order and read its history as you look further away. Said a different way, what this allows us to do is to reconstruct the third dimension of the universe. This basic structure is what underlies all of modern cosmology, and it has been wildly successful. So the Hubble expansion law is one thing, okay? But out of this basic framework, which was taken by applying Einstein's theory of general relativity to cosmology, we learned that the early universe had to be hot, and I'm going to say a lot more about that soon, and radiate at a certain temperature. Don't worry about this picture, I'm going to explain this to you later. We also were able to get a very precise prediction of the abundances of the light elements, something I won't talk about here. So all of this is meant to say that this theory of the Big Bang, as it's called, has been wildly successful and really was the start of a new era in science, all based on Einstein's theory of general relativity. But this theory and this set of observations pose its own problems for matter and in fact for gravity. Okay? If you go out into the universe and you measure a sufficiently big part of it, many times bigger than galaxies or clusters of galaxies, and you weigh it, which we can do using modern cosmological astronomical techniques, you discover a remarkable thing. You discover that only 4% of the universe is made of atoms, the kinds of stuff we know of. Another 22% is made of something that we know clumps up in a certain way, but we don't know what it is yet. We have some ideas, but no proof of what it is yet, and it's called dark matter. And remarkably, another 74% of it is made up of something that seems to be causing the expansion rate of the universe to accelerate, something we call dark energy. And I won't talk about that at all today, really, except maybe just hinted at the end. But that's an entire other lecture that I've given many times. And then there are a whole bunch of other questions that I won't have time to talk about, which I might call origin questions. Why is the universe so flat? Why is it so almost homogeneous? I told you on large scales, the universe looks the same everywhere. How come? And why did galaxies form? And I'll say a little bit more of that later. For now, because I want to talk about the things that gravity does for us and how we can test it, let's focus on just one part of this diagram, the 22% of the universe that is dark matter. And let me tell you a couple of interesting things about the dark matter. So I told you that one of the original successes of general relativity was a postdiction. People had known that Mercury behaved in a certain way, and Einstein came along, gave you a theory that explained that. So that was wonderful. What's great about theories, of course, is to have a prediction. The theory tells you something and you go look for it. And one of the early insights into dark matter are actually fueled by data that goes back to the very first original test of general relativity performed by Eddington. So here's the headline from the New York Times that the day that this was announced: lights all askew in the heavens, men of science more or less agog over results of eclipse observations. You know you're in the last century when it talks of men of science. And amazingly, what Einstein had said is, well, back when we talked about needing to recover conservation of energy, we noticed that light had to be affected by gravity. And what Einstein found was not only is light affected in that it loses energy or gains energy, but it's affected in a similar way to the way that massive particles are affected by the presence of large objects. We know that if we take a large object and a massive particle comes by, it will bend as it's attracted to the large object. Amazingly, Einstein showed that that also happens for light. And it happens not really because it's attracted to the object, it happens because the big object bends up space and time, and this curved path is a straight line, really, in that bent up space. So one prediction of this from Einstein, from Einstein's theory, was that during an eclipse, when you look at stars, you should be able to see their position move as light rays pass close to the sun. And this is what Eddington observed. So this is called gravitational lensing, and I'll show you why that is now in a much more modern context to do with dark matter. So how do we apply this to cosmology? Well, we know what the universe should look like. We know what galaxies should look like far away in the universe because we know what galaxies look like close by in the universe. So if you're looking at, here's our sky, if you're looking at galaxies far away, the light from them, as it comes to us, passes by many other massive objects. And because of that, that light will bend. And because it bends, it will distort the image. And so in modern cosmology, what we can do is we can look at the observed sky, compare it to the statistical properties of the ideal sky, and infer what kind of stuff got in the way. So before I show you this in reality, let me show you it in a toy example, which I think will be much clearer. So here's a picture we all know. Here's a picture of Einstein, and you should imagine that you're sitting looking at your screen right now, and the light rays come from this picture, and they come directly to you, essentially in a straight line to your eye, and your eye constructs this image. And now what I'm going to do is I'm going to take a tiny black hole, so small that you can't see it, and I'm going to place it just in front of Einstein's nose. And this is not an artist's impression. I'm going to use ray tracing to actually construct what you would see if I did that. So here's Einstein. Here's what you would see, the light rays that would make it to your eye if I put a tiny black hole right in front of his nose. So there's some things to notice about this picture. There's a bunch of stuff in the middle that I don't want to talk about. You see multiple copies of Einstein here, upside down, back to front. These are in what you might call the strong lensing regime, light that is passing so close to the black hole that it's going many times around the black hole before it comes out and hits your eye. But far away from the black hole, remember I'm putting the black hole right in front of Einstein's nose. So far away out here, you see that everything gets bent into arcs. And this is the generic thing that happens. This is called gravitational lensing. You'll recognize that it looks not so different to what happens when you put an actual glass lens in front of something. And this arcing is something that's generic and happens all the time when gravity affects light coming from faraway objects. So you might imagine that you could do the following. If you knew what you were supposed to be looking at, and I gave you this picture, you could ask the question, what distribution of matter and energy had to be in the way so that when the light rays that I would have seen from here bent around that object, this is the set of light rays that came out. And from that, you could infer, it was actually a small, massive object, a black hole right in front of his nose. It turns out in cosmology, we can do the same thing in a much more complicated way. So here's a picture taken from the Hubble Space Telescope of a very small patch of the sky. And I want you to focus over here. What you're seeing here is something quite remarkable. Almost every speck of light in this picture, by the way, almost every, not every, is a galaxy. And what you're seeing over here is a cluster of galaxies in the foreground. And a little further away, you're seeing light come to us from galaxies that are very far away. And you see all these arcs? All these arcs are the gravitational bending of light around this cluster of galaxies from faraway galaxies. And we can do with this picture what we do with the Einstein picture I told you. We know that galaxies are not really shaped this way. So you can ask, what's the mass distribution in this cluster of galaxies that's in the way that causes these arcs to develop? And the way you do that is by plugging this data along with Einstein's equations into a supercomputer. And here's what you get. So let me go back a second, show you this one more time. On the sky here, there are two angles as you're looking at it, this way and this way. So I'm going to show you what you reconstruct for what's in the way in the same coordinates. So here's what you get from a supercomputer. Again, here's the angle that way, and vertically is plotted how much stuff is in the way to cause that exact warping of the pictures of faraway galaxies. And from this picture, you should take away two things. Firstly, there are lots of spikes. What are those spikes? Those spikes are the galaxies. I told you it was a cluster of galaxies that's in the way, and we can see many of those galaxies in the light. And so it's not surprising that we also see them when we reconstruct where the mass is that caused the lensing. What is much more surprising is that superposed on top of these spikes is a much less spiky but huge increase underneath of overall mass. You see that? It's smoother, goes up and down, nothing to do with the spikes themselves. And that is something that you do not see in the light, and yet its total contribution to the energy and mass that's causing the lensing is much more than each of the individual galaxies. That is dark matter. So what you're seeing here is something quite remarkable. You take observation of gravitational lensing that we know exists because of Einstein's theory, you solve the complicated equations on a computer, and what general relativity, gravity, has taught us is that there's a new component of matter in the universe, and it's called dark matter. Furthermore, we know that this stuff is really particles, but I'm going to actually skip these slides because I'm worried that I'm going to run out of time, but I can come back at the end if you want to. And so the question for people like me is when you're faced with views of the universe from ever more accurate telescopes like this one, then when you really analyze what you're seeing in an image like this, all the little arcs, etc., you learn that what underlies this is a distribution of matter and energy that is bending up space and time in a very peculiar way. And you have to ask, what is causing all that bending up of space and time? Okay. General relativity seems to pass this wonderful test, this test of gravity. It tells us how things are behaving, but it leaves us with a huge question. What is this stuff that's in the way? We could see the galaxies, but what is the stuff that we couldn't see that we were only able to find by doing this lensing measurement? Not only, but one way to do it is this. So that's one thing that gravity does for us in cosmology. It teaches us that there's a huge part of the universe, many times the amount of the universe that's made of the kinds of matter that we're made of, out there, everywhere, and we don't know what it is. What else does it tell us? So to talk about that, I'd like to go much further back in time. So dark matter played its biggest role in the universe, actually, when galaxies were forming. Cosmic acceleration, which I mentioned in passing, is an even later phenomenon, and that teaches us a lot about general relativity. And I could give you an entire other lecture about it, but I won't do that today. Instead, what I want to focus on now is the very earliest times in the universe and what that might tell us about gravity. And to do that, I want to remind you of something. I told you that the universe is getting bigger today. I told you that faraway galaxies are moving away from us. And if you think about that for just a moment, you'll realize faraway galaxies are moving away from us. Therefore, in the past, they were closer to us. Therefore, in the far past, they were very close to us. And in the very, very far past, they were so close that all matter in the universe bangs together. And you know what happens when you take a lot of matter and you bang it together and make it very dense? It heats up. So if you knew nothing about general relativity or modern cosmology, you would have no reason to believe that the universe was hot at any point in its history. But once you know about general relativity, once you know about Einstein's theory, and you apply it to cosmology, you're forced to realize that the early universe had to be small and dense and hot. And it's that we call the Big Bang. But it has some very profound consequences. Hot things glow, okay? You know that, right? We know that when something has a particular temperature, like this oven top, then it will glow. And what's even better than that, what physics teaches us, is that the colors that they give off, the spectrum of light that is emitted when they glow, is a unique signature of the temperature that they have, okay? And so you can split up light into not just the visible here, but the X-ray and the gamma ray and the ultraviolet, infrared, microwave, radio, etc., as you go from long wavelengths, low frequency, to short wavelengths, high frequency. And you can figure out by how much of each of these types of light is in the emitted spectrum of an object, how hot it is. And the universe should be no exception. So what does that imply? What does that imply? If hot things glow and the early universe was hot, what does that mean for us? Well, it means that the early universe glowed at a hot temperature. And I've drawn here just a schematic. I've drawn the universe as a ball, and I've drawn one wave of light going around. As it expands, that wave expands. And so the wavelength increases and the frequency decreases. And so what that means is if you have light at early times in the universe of a given frequency or given wavelength, then as time goes on and the universe expands, that frequency will decrease and the wavelength will increase. And of course, if the frequency is high, the temperature is high. And if the frequency is low, the temperature is low. What this means, therefore, is that if the Big Bang Theory is right, the early universe should not only be hot, but the temperature should change over the history of the universe, and it makes a precise prediction of what we should see in the sky today. The prediction is that we should see a spectrum of radiation, so-called black body spectrum, the characteristic spectrum emitted by any object purely by virtue of their temperature. And that temperature today should be around 3 Kelvin. And in 1964, these two gentlemen, Onno Penzias and Robert Wilson, discovered this radiation. In fact, what Penzias and Wilson were doing, working at Bell Labs in New Jersey, were looking for noise. They were trying to build the world's most sensitive radio antenna, and they were looking for noise in their radio equipment, and they were trying to get rid of that noise. And in fact, their paper talks about how they tried to clear out what's called white dielectric material in their receiver, which was just, there were lots of birds around and birds kept dropping into the antenna. And they tried everything to get rid of the noise and they couldn't get rid of it. And of course, by discussing with nearby collaborators at Princeton and other places, they figured out that in fact, what they had found was not something they could ever get rid of. It was the temperature of the universe, the microwave background radiation. And here I'm showing you that radiation from a later experiment from the early 1990s called COBE, where this exquisite measurement of a black body spectrum was measured. Now, why am I telling you about this? It's another wonderful validation of the idea of the expanding universe, which we're forced into by general relativity. But the reason I'm telling you is that this is not the end of the story. And in fact, in modern times, we can do remarkable things with the microwave background. We can measure its little fluctuations from place to place. It turns out it's not exactly the same temperature everywhere, but it's very close to the same temperature everywhere. And so what you can do is you can measure the temperature in microwaves of the entire sky. And then you can do it looks like this, by the way. And then you can do very clever things. You can remove all the individual point sources here, little objects that are not the universe. You get rid of them. Now you're left with this. But then you've got the Milky Way that's in the way, in the middle. And that's a problem. So you get rid of the radio emission from the Milky Way. But then the Milky Way is full of dust, and the dust itself emits light in the microwave. So you want to get rid of that emission, and you can strip that away. And what you're left with is just this. It's a picture of the temperature of the universe. It's in the microwave. The difference between temperature between the hottest parts of this and the coldest parts of this is 1 part in 10 to the 5 or 10 to the 6. It's incredibly uniform, but these tiny fluctuations contain masses of information about the universe. So there are two things that we learn from this radiation. One is the universe is almost at exactly the same temperature everywhere. That's one thing I'd like you to keep in mind. And secondly, superposed on top of that are tiny differences in temperature from place to place, which will be important when we speak later. it turns out, is an enormous problem. Here, I'm showing you a picture of the universe as seen from Earth. Now remember, the universe is expanding, distant galaxies are moving away from us, and in the past, they used to be close to us. So when you observe things far away, the further away you look, the further back in time you're looking, because it's taken time for light to reach you from further away. And it turns out that when you look 15 billion years or so away, you can see the universe at an age of about 300,000 years, and that's the age at which the microwave background radiation was released. Okay. Here's the problem. If I look at 2 points on the sky, over here, and I measure its temperature, and over here, and I measure its temperature, in fact, any 2 points on the sky that are separated by more than about a degree or so, they radiate, as I told you a moment ago, at almost exactly the same temperature. But the problem is that if you trace the evolution of the universe backwards, as we understand it, those 2 points in the universe were never in causal contact with one another. So we all know that if I handed you an object and it was the same temperature everywhere, you would assume that that object had had time to equilibrate. Things don't just become the same temperature. Okay, if you introduce some cold air into a room, now you've got a room with cold air and hot air in it. Eventually, it'll all have about the same temperature. But the reason that happened is that there was time for the different parts of the room to exchange heat and reach a common temperature. Here, you've got 2 points in the universe that never had time to communicate causally in the history of the universe, and yet they remarkably radiate at the same temperature. This is one of a number of problems that faced people in the mid to late part of the last century. And this one is called the horizon problem, and it's a biggie. Now, our best example, our best hope for solving this problem at present is an idea called cosmic inflation. Inflation was developed by several different people, but perhaps most famously by Alan Guth at MIT. And you can now go to the Adler Planetarium in Chicago, and Alan's notebook from the day he realized that this might work is, you can see it behind glass in the museum. And he has this hilarious thing where he wrote at the top of his page, spectacular realization, which, you know, we should all do on every page of our notebooks, I guess. But what Guth had realized, and others too, was that if the universe at its earliest times underwent an accelerated expansion, so, you know, the universe is filled with stuff, bodies, and even though it's expanding, all of those bodies attract each other and should slow down the expansion of the universe. What Guth noticed was that if there was a period where that wasn't true, if the universe expanded more quickly over time, acceleration, just for the blink of an eye at the earliest times in the universe, that would be enough to solve a number of these problems like the horizon problem. So this idea, cosmic inflation, which has become really a cornerstone of modern cosmology, although by no means proven yet, makes the universe grow unimaginably large in a minuscule amount of time. I won't even begin to tell you how small those times are, but they're very small. If that's true, then our observable universe that we see today, even though it's unimaginably large, came from a tiny, tiny patch, so small that it was very easy for it to have reached the same temperature at the same time. And so this is how it solves the horizon problem. It did have time to equilibrate in the early universe, gets blown up over a fraction of a second to become bigger than the observable universe today. And now it's not surprising that everywhere in that big patch has about the same temperature, because it came from a tiny patch which easily could have the right temperature. As is becoming a theme here, this remarkable solution of a problem comes equipped with its own problem, okay? Namely, remember when I showed you the microwave background? Let me not do that because I don't want it to play. But at the end, the microwave background had tiny little variations from place to place. But inflation would never do that. Inflation would give you the exact same temperature everywhere. Why would there be little differences from place to place? And that is an amazing story that I sort of want to be one of my last things I want to say today. Okay. So it turns out that everything we've been talking about, the universe, gravity, heavy objects, their effects on light, etc., really is going to come down to the physics of the tiny, quantum mechanics. So remember what I told you about inflation. The universe starts out unimaginably small, a tiny patch of it. There's some mysterious behavior, which I have not tried to explain to you, called inflation, which blows it up to a huge distance in a very quick time. And then it slows down and just keeps expanding more slowly. And that expanding more slowly part is the normal Big Bang. Everything I told you there was classical physics, but of course, there's no such thing as classical physics. Quantum mechanics is always there in the background, at least. And here's what's going on with quantum mechanics when you try to take it into account when that's happening. While the universe is growing very quickly, quantum mechanics is causing little bits of matter and energy to flutter in and out of existence from place to place. Here I've shown just an example where there's a little bit less mass and energy here and a little bit more mass and energy here. By the way, this is happening all the time, all around us, in the room that each of you is in right now. But because the universe is not doing anything strange, those things just flutter in and out of existence all the time. They remain quantum mechanical. But in an accelerating universe that accelerates very quickly, before these things can be reabsorbed, if you like, by the vacuum, they grow. And now there's a somewhat bigger fluctuation with a little bit less mass energy here and a little bit more mass energy here. And again, the expansion rate is very, very fast. And so eventually they become very big fluctuations with a little bit less mass energy here and a little bit more mass energy here. And now they can take enough energy from the background space-time to become real fluctuations and imprint themselves on the space-time. And so amazingly, our best guess is that when you look at the microwave background and at later times you look at the structure of matter in the universe, some galaxy clusters over here, maybe a void over here, the origin of all that seems to be not classical physics, but quantum mechanics writ large on the sky. So there's a popular quote from Carl Sagan is that humans are the stuff of stars. And by that, he means that you're all made of carbon and oxygen and elements that were all made in supernovae in the first generation of stars. What this story that I've told you teaches us is that if inflation is correct, those stars themselves owe their very existence to the energy of empty space that was dragged into existence by the brute force of gravity. General relativity forcing quantum mechanical fluctuations to become real fluctuations in the sky, which we then measure later as more matter here than there is. This means that the beauty of the universe is that on the largest scales, when you look across the sky, you're reading really secrets of the innermost parts of the atom that have been spread out along the sky. I think it's quite a beautiful story. And the goal for modern cosmologists is to try to read that story properly, because it's going to teach us everything we may ever have dreamed of knowing about the rule book of nature. So before I finish, I will explain something really very modern from this, which is that this idea that inflation may teach us about the most enduring puzzles of modern physics is something that is particularly exciting today, because it provides us with an exquisite new test, again, really using gravity. Okay. Everything we know about physics tells us that the gravitational field itself, or if you like, the metric, given that we've learned about general relativity, should be quantized. You know, Maxwell taught us about the electromagnetic field, and now we know that really the electromagnetic field should be quantized, and it has quanta that are called photons. And we know that's true of all particle physics. All of particle physics is described by quantum field theory. We also expect that the gravitational field itself should behave the same way, and there are many, many good reasons to believe that. Okay. But if the gravitational field is quantized, it should have quanta, and those quanta should be gravitons. Now, I told you, well, let me just go on. So then, let me not ignore that equation for now. So I told you that inflation amplifies quantum fluctuations of matter, but it should also amplify quantum fluctuations of the metric itself. So why that universe was undergoing that massive acceleration, not only was it making a bit more matter here than here, it should have been making variations of the metric here and variations of the metric here, okay? So there should be wiggles in space-time on top of all this matter that are being generated. And the most promising way to measure these is by their imprint, again on the microwave background radiation, but not on its temperature, but on what's called a polarization. So the light coming from the microwave background is not only a given color, but it can be polarized, and it can be polarized in many different ways, depending on the kinds of matter it's encountered on its way to us. But there are particular types of polarization which cannot really be generated by other physics, and mostly only arise due to being imprinted by fluctuations in the graviton itself at early times. So there's a unique prediction. The simplest models of inflation, not all inflation, so that's a problem here, but the simplest models make a prediction. They predict that there should be fluctuations in the gravitational field, not just in matter, from place to place in the universe. And you should be able to measure them by polarization. And there should be a ratio of two quantities here that I won't go into in details, but basically the amount of fluctuations in gravity compared to the amount of fluctuations in the temperature. And they should obey a particular relationship that relates them to how inflation happened. This epsilon is a feature of how inflation happened. So in the present day, when we're just starting to make exquisite maps of the polarization of the microwave background, this is something that you may see happen in the coming decades. You may see that we measure this, and it might not turn out to be this, which would not kill inflation. But if it does turn out to be this, then what you will have seen is the first ever measurement of the quantum nature of gravity. And that would be a truly remarkable thing. So keep your eye for hints along the path to that eventual test. Last comment. I told you that the universe is accelerating today. I don't want to, and let me not stay on this slide. Let me say the following. The universe is accelerating today, and it could be accelerating because of a new form of mass energy called dark energy, which I said in my original slide. Or it could be that Einstein's theory of general relativity itself now needs modifying finally after a century. We don't know the answer to that question, but amazingly, in the last few years alone, we now have a completely new tool, gravitational wave astronomy. Okay, you look, for example, at binary systems, be they binary black holes, black hole neutron stars, neutron star binaries. You look at how space-time is bent and wiggling as these things collide, and you can read off the waveforms. I'm sure you've all seen these. There's certainly a lot of action going on in India now in gravitational wave astronomy, and this is another prediction of general relativity that has been directly measured. But it turns out that this can actually also be turned into a tool. Okay. And I just want to give you one example. One theoretically robust idea for challenging general relativity to explain cosmic acceleration is massive gravity. I won't tell you anything about it. All you need to know is that theorists are very creative, and they've created a web of strangely named theories, all of which are hoped might provide a way to explain why the universe is accelerating. And these theories were starting to grow ever more baroque, and many of them were many different tweaks on previous ideas, and who knew where this would end. But once we've had observations from LIGO, Virgo, and Dark Energy Survey of things that you can observe in light and you can observe in gravity waves, it turns out that that alone kills huge numbers of those theories. And in particular, just 4 years ago, less than 4 years ago, a single event, gravitational wave 1708-17, and gamma ray, which is its optical counterpart, gamma ray burst 1708-17A. That alone, by measuring how light and gravity simultaneously behaved, was enough to rule out huge amounts of theoretical musings about what might explain cosmic acceleration. So I haven't talked about the theories of cosmic acceleration here. What I wanted to tell you in the spirit of this talk about gravity is we now have completely new tools, and that's going to have profound impact on our theoretical development. So let me summarize. I think I've been talking for about an hour. We spent over a century testing GR, and precisely a century or so since Eddington's original measurement of light bending. Modern cosmology and astrophysics are providing us with ever-improving measurements and entirely new tests of general relativity. So it's a very exciting time to be thinking about these ideas. But the last few years have perhaps been the most exciting, although because of gravitational waves. Although cosmology may hold even more tests and surprises as we look at the earliest times in the universe. So gravitational waves are a new tool, that's very exciting, but it might be that ultimately they and our precision measurements of the microwave background are going to teach us that the earliest times in the universe behaved in a fundamentally quantum mechanical way. And that would be a remarkably exciting observation. And so to those of you who are students who are thinking of working in this field, you should fasten your seatbelts. You're in at the beginning of what's going to be a very exciting few years, I think. Thank you.
So if anybody has any questions, then they can unmute themselves and ask now. Okay, I guess I'll go first. So I had a couple of questions. You talked about inflation, which we had introduced for solving some of the problems in Big Bang. So I wanted to know a bit more about inflation, like what caused it, or how do we, or the explanation for the inflation.
Yeah, so there are many, many models of inflation. So, but the simplest idea, which is still the one that really captures most of the relevant physics, is a very simple one indeed, which is that, you know, fields in the universe, distributions of mass and energy, have two components to their energy, three components to their energy, typically. They have their kinetic energy, the gradient energy. If the value of a field here is different to the value here, then there'll be a gradient energy. And then they have their potential energy. And it turns out that each of those can cause the universe to behave in different ways. But if you can arrange it so that a field in the universe has negligible potential energy, therefore it's slowly moving, negligible kinetic energy, therefore it's slowly moving, negligible gradient energy, and therefore it's very smooth, therefore it's dominated by its potential energy, that will drive an accelerated period of expansion like inflation. So that's our best guess for what drives inflation. The potential energy of some scalar field in the universe, some very simple version of the Higgs field, for example.
Okay. Another question is, you talked about a test for quantum gravity, which is the ratio 16 epsilon. So is that quantum gravity a specific quantum gravity or just a general theory?
Yeah, that's a good question. So I think you're asking, you know, could we learn, is it string theory or is it something else? I think making that measurement alone is not guaranteed, I should say. It's going to be a very, very hard thing to measure alone. So I think the idea that we'll measure it and measuring it alone tells you nothing about what theory of quantum gravity. It just tells you that the graviton was quantized. Now, could you make measurements about the early universe that would allow you to distinguish between theories of quantum gravity? Perhaps. People certainly come up with ideas, tentative ideas, the ways in which one might do that. But the example that I just gave you, no, that does not distinguish between different theories of quantum gravity.
Okay. So we also had a few questions from YouTube. One person asked, so in the initial stages of the inflation, does it mean that unreal particles become real because of the rapid expansion? I'm not sure what that person means exactly.
Yeah, so yeah, it means that virtual particles become real. Yes, that's right. And it means that means that another way to say this is that space-time is very, very curved. Space-times can have a temperature. Okay, so For example, when the phenomenon is not so different really to the idea of Hawking radiation, why black holes radiate. Space-time is very curved and it has a temperature. But yeah, one way to think about it is that you're producing particles virtually, and the expansion of the universe allows them to take energy from the expansion and become on shell, to become real particles. Yeah.
Okay. And the question is, just a minute. So, what does it mean for vacuum to have temperature? Is it due to the radiation, perhaps? And if so, then how can we explain that? Since the expansion is faster than the speed of light, so I think how do we assign, like, explain radiation to parts where the radiation hasn't reached?
Okay, so there's lots of parts to that question. So first of all, just to be clear, the radiation is happening everywhere. Okay, the universe. Can someone turn their microphone off, please? Okay, thank you. The radiation, the universe is not expanding from a point. Okay, the universe is expanding everywhere from a point in time. So this temperature is everywhere. It's not that it reaches it, it's everywhere, okay? The radiation is everywhere. So, when radiation reaches us from a place, 15 billion light years away, that was hot and it's cooled on the way here, there's radiation reaching that point now, which came from originally where we are now, that was hot then, okay? So it's not that there's places in the universe waiting to get radiation. Everywhere has the radiation. Also, it's not correct to say the universe is expanding faster than the speed of light. Okay, this is a very curved space-time. Relative speeds are only really something that makes sense in a flat space. So it's not really true that things are expanding faster than the speed of light. But I think what you mean is that there's a horizon, and outside of that, things have not communicated with things inside of that. But they've communicated with other things in their own horizon, and that's enough for them to see the microwave background radiation. Is that the whole question? I'm not sure. I couldn't remember all of it.
I think so. So that's the question. Does anybody else have any question?
I have a question.
Uh-huh.
So I've read that dark matter must be slow moving to influence the properties of our universe. So can we predict that dark matter must be relatively cold in nature?
Yeah, so it's a good question. Yeah, so we do expect that the best candidates that seem to fit the data best are what's called cold dark matter. So exactly what you said, matter for which its kinetic energy is much, much less than its rest mass. Now, when you say, can we predict that? That's what we measure. We measure that that's the best fit. What we're looking for is a theory that will predict that. And there are examples of theories that predict that. Some supersymmetric theories have lightest supersymmetric partners that behave that way, but there are many, many, many other examples. So I would say the hard thing is not so much getting a theory that gives you a slow moving dark matter candidate. The hard thing is getting a theory that we can test, that makes sense, that fits into our other theories well, that has the right properties to give us a slow-moving dark matter candidate. And there are many candidates, but there are no compelling answers right now. But indeed, you're right. It doesn't have to be, but the best fit models are cold dark matter, slow-moving, massive particles. Did that answer your question?
Yes, sir.
Thanks.
So I had one more.
Oh, sure.
So I have read that this inflation can explain uh, a few problems, such as mainly three problems: the horizon problem, the flatness, and the magnetic monopole. So, do we have any other theory to explain this, or is it just the only theory that we have to explain these?
Yeah, that's a great question. So I think it depends who you ask, really. There have been some proposals, bouncing universes in particular, that grew out of a proposal called the ekpyrotic universe that some of my colleagues developed. Each of these proposals has their own problems to overcome. Inflation is certainly the best developed and best tested idea. But there, like I say, there are some other ideas. From my perspective, one of the hardest problems here is that it's a very difficult thing to calculate what happens in the Euler universe. And partly that's because you might expect the Euler universe to be quantum mechanical purely. And then we don't really know how to calculate in a quantum theory of gravity. Inflation has the great advantage that it makes sense as a theory of quantum field theory, weakly coupled to gravity, where you can use what's called the semi-classical approximation to quantum gravity, and that's enough to get all the answers you need. It could be that there are many other clever ideas for what happens in the Euler universe that involve real quantum gravity effects, but we just don't know how to calculate them. And so that's something I spent some of my time thinking about, in fact, whether you can use clever techniques to get at quantum gravity effects in the Euler universe. But so far, inflation is by far our best tested and best developed answer. It does a lot of things very, very well, and it has some questions left over. The bouncing universe idea is somewhat well developed and has its own problems, but I think some would argue its own promise. And we don't have any other very well developed examples, I would say.
Okay, thank you.
Sure.
Excuse me, sir.
Yes.
So due to gravitational lensing, so light is deviated. So how do we know the extent of deviation to know the exact location of that distant object?
So I'm sorry, could you say that again just a little bit more slowly?
Okay, sir. So due to gravitational lensing, we know that light is deviated. So how do we know the extent of that deviation to know the exact location of that object?
Well, yeah. So it's complicated. You have it's a very good question. Okay, so I gave you a very simplistic picture of what's going on. What really happens in these setups is you use statistical knowledge of what the universe looks like and compare that to the statistical features of the sky that you observe. And so each individual object, you do know what's going on with it, but you're right, there can be some degeneracies over how big the object is that's causing the lensing and how far away it is. But you can solve that by using many objects, and it's really the statistics of the sky that you're using.
Okay, thank you.
Sure. Well, it seems like we might have exhausted the questions.
I guess so. If we don't have any more questions, then we can end this meeting.
Well, thank you very much for having me. I enjoyed giving the talk, and it's been nice to see so many people interested in this kind of thing.
Thank you for giving the lecture as well, sir. I'm sure you would have had a very busy schedule, and you have taken time out of that schedule to give us this wonderful lecture, and very interesting as well.
Thank you.
Many have also thanked you for the lecture. Also, thank you everybody who has attended this lecture. Yeah. Thank you to you too as well, sir.
Bye.
Goodbye, sir.